In example 8, we're going to discuss the continuity of the piecewise functions, okay? So piecewise functions. So what we're going to be able to do is tell what the function is doing as it comes in from the left by plugging this value in to one of the functions, whichever function it is as it's approaching from the left, okay? So let's study problem A to start with. And on problem A, you'll notice that it's this function, the x squared plus 2x minus 3, when x is less than or equal to 1. So this is going to be the function from the left and where the function is equal to 1, okay? The 2 square roots of x minus 1, where x is greater than 1, is going to be the function coming in from the right, but not where the function equals 1, okay? So let's take a look at the first part, okay? So problem 1, all right, as this function approaches 1, so the first thing that we're going to do is our first definition is f of 1. So at 1, if I plug 1 into this, that's 1 squared, so that's 1 plus 2 times 1 is 2 minus 3. 1 plus 2 is 3, minus 3 is 0. So the function at 1 is 0, okay? Easy enough. The second part, I need to figure out the limit, okay? Well, as this guy approaches 1, this is coming in from the left. Well, we discovered that as it goes to 1 from the left, it's going to go to 0 because this is the point with the or equal to on it. So this is going to go to 0, okay? So the limit, let me write this all down. So the limit as x goes to 1 from the left of the function is 0, okay? Because that's where the function is heading at 1, and it's where the function is heading from the left. So these are both equal at 1, okay? But now we need to look at the limit as x goes to 1 from the right, okay? And this is a tiny bit more difficult. We're going to use this function from the right. So if I plug this in, we're going to get 1 minus 1, which works out great because 1 minus 1 is 0, and the square root of 0 is 0. 0 times 2 is also 0. So this limit from the left and the right are both 0. Now, if they had asked me a number that was not 1, so let's say that they had asked me something on this one that would have given me a negative square root, then we're going to have an issue, so we're going to have to look at that for issues with the domain like we talked about in 2.1. But it didn't work out that way. So I've got the limit as x goes to 1 from the left is 0, and the limit as x goes to 1 from the right is 0. So therefore, I could say that the limit as x goes to 1 in general is 0. And this statement right here, the limit as x goes to 1 of f of x is 0, is the only statement that you really need for part 2. I just wanted to make sure you saw where I was getting these from. Okay, so this one's from the left. This one came from plugging it in to the right. Okay, then let's look at 3. Part 3 says that this limit right here that we came up with should equal the function. So the function at 1 should equal the limit as x goes to 1. And the function at 1 we said was 0. And the limit at 1 we said was 0. So this is a true statement, okay? So then we would say, therefore, f of x is continuous at x equals 1. Now notice we didn't say it's continuous everywhere else because we don't know if it's continuous everywhere else. But the point that we checked, f of 1, it is continuous, okay? And they wanted me to justify by sketching the graph. If you feel the need to sketch the graph, you can. I don't feel any need to do that. You can put that in the calculator and just take a look at it and compare, make sure we're on the same page, okay? So taking a look at B, we're going to do the same type of thing. So look at this one. So this right here, x is less than negative 2. So I know this is from the left. This one says x is greater than or equal to negative 2. So this is the equal part, and it's the part from the right. Okay, so this is the left, this is the equals and the right. And we're going to do where x is negative 2, okay? And most of the time you'll see piecewise discussions of continuity. They'll only talk about this point where the two pieces should meet, okay? Because if they meet like this, then they're not continuous. If they meet up, then you're fine. So that's really the only part we care about. So let's look at this function. X at negative 2 is going to be, this is the equal one, so f of negative 2 should be the one that's equal. So if I plug negative 2 into this, This is 1/2 of -2 squared. -2 squared is 4. Half of that is 2. 2 minus 3 is -1. Okay, so f of -2 is -1. For part 2, I'm going to write it all the way out again just so that you can see. I need to do the limit as x approaches -2 from the left. And if I'm doing the one from the left is the one on the top. So if I plug -2 into the one on the top, this is 6 over -2. 6 over -2 is -3. So the left goes to -3. The right goes to the same one as the bottom because that's the or equal to. So the right would be where I would plug -2 in again. And remember, we already did that and got -1. So from the left, it goes to -3. From the right, it goes to -1. So the limit of this function as x goes to -2 does not exist, which tells me that as this piece comes in from the left, it's going to -3. As this piece comes in from the right, it's going up here. So they're not going to actually meet. There's that giant gap. It's called a jump discontinuity. So I would say, therefore, f of x is not continuous at x equals -2 because the limit as x goes to -2 of the function does not exist. Okay, it does not exist. And if they asked you to be more specific to talk about what type of discontinuity it was, you could say it is a jump, well, non-removable jump discontinuity. So if they asked you to describe the continuity, since the limit doesn't exist, you know this piece is going down here, this piece is coming up here, so there's a jump, okay? So you'd have to look for that part. And then we'll discuss the next section in another video.